Alright guys, this is 19.7. The problem says a copper rod and an iron rod with the same dimensions are welded together end to end. The outside end of the copper rod is 100 degrees Celsius and the outside end of the iron rod is 0 degrees Celsius. What is the temperature at the midpoint where the rods are joined? Alright, so we're going to start like we always do by writing what we want, which is the temperature at the junction the rods are joined at. So in this picture here you can see we have the copper rod on the left with the end being 100 degrees and the iron rod on the right with the end being 0 degrees. And in the middle, that scribbly part is the welding point where they're joined together, and we're looking for the temperature at that part. All right, so things we know the constant for the constant of heat flow for copper. We know the constant of heat flow for iron. We can see copper is a lot more conductive than iron for heat. We know that the rate of change of heat transfer with respect to time is equal to the constant times cross-sectional area of the rod times the change in T over L, or change in temperature over L, length of the rod. So we know this to be true. And then this is another important part of the problem. We know that the rate of change of heat flow with respect to time for the first part of the rod is going to be equal to that of the second part of the rod. In other words, the dq dt for copper is going to be equal to dq dt in the iron part of the rod as well. So that's going to help us find the temperature in the middle. All right, so substituting in this term for dq dt and making this term a bit more specific. So on the left, dq dt1 is going to be dq dt for copper, and dq dt2 is going to be that of iron. So we can say the constant of copper times cross-sectional area rather than just having the general constant. So that term is equal to the term respective to iron. And then just simplifying that, first we're going to break up the delta T into its parts, which is temperature at one point minus temperature at another point. We can also do some simplification since the problem specifically says that the rods have the exact same dimensions. Cross-sectional area and length in this equation are irrelevant, and we can cancel them out. That's why they're on both sides of the equation. So that leaves us with this. KCU times T final minus T initial is equal to KFE times T final minus T initial. Cu and Fe are the chemical symbols for copper and iron, by the way. All right, this is probably the most confusing part of the problem. So I normally don't substitute in numbers until the end, but I'm going to here because we have a 0, so that simplifies things a bit. So basically, the reason we go from TF and T initial just to the general term T here, the reason we can do that is because the final temperature for one rod is going to be the initial temperature for the other rod. So basically that means the initial temperature at one end of the rod is equal to the final temperature at the other end of the rod, or at the midpoint. So since at the midpoint, which is the point we're interested in, Ti is equal to Tf, we can just take off the subscripts or the separation of those two variables, and we could just call that T generally. And this is important. This is probably the hardest part of the problem. It tripped me up when I first did it, because you won't be able to solve for a single temperature at the midpoint unless you catch on to that. So substituting in numbers, we have a 0 on the right side for the iron end of the rod, and we have 100 on the other side. Simplifying a bit, we have this. And then we're just going to rearrange so that we can get all the terms with the temperature in them on one side of the equation. So we're going to get KCU times 100 is equal to KFE times T plus KCU times T. And then now that we have all the temperature terms on the right side, we can factor out the T, which is what we want to do because T is what we're looking for or what we want to isolate for. So we factor out T, and then we're just going to isolate for T algebraically. And again, as I mentioned with the midpoint thing a couple of seconds ago, T is the T at the midpoint or the junction. So T is going to be equal to KCU times 100 over KFE plus KCU. So that's the answer. We know it's the answer because it's what we want in terms of only known values. And then if you want, you can substitute in the numbers to get about 83 degrees Celsius as the temperature at the midpoint of the rod. So tricky parts of the problem we already went over. As far as the context of the problem, it's just trying to get you to understand thermal conductivity and how we can manipulate equations to solve for temperature at certain points in a rod. or in any object for that matter. Uh, Other confusing parts, this dq/dt is something you might not have seen as much before, or at least I haven't. But again, it's just the rate of change of heat transfer throughout the rod, and we know that, again, from this equation, that the heat transfer is equal throughout all parts of the rod, or the rate of change of heat transfer is equal. All right, thanks, guys.